Today we're going to be talking about rates of change, which is really one of the big ideas in calculus. And we're going to start by looking at the average rate of change. And I've got a formula in my notes that defines average rate of change to be basically a change in outputs divided by a change in inputs. Now this formula might look a little familiar to some of you, and in fact it should be familiar. This is actually the slope formula. Recall slope is change in y divided by change in x. You might have learned it in a slightly different formula. When you learned slope, your formula might have looked something like this. But it's really the exact same formula. I'm just using function notation. So I'm taking a change in outputs divided by a change in inputs. So let's take a look at a specific example. Example 1 says the distance of a bike t seconds after it starts moving is given by the function d of t equals t squared. So d, or the outputs, is distance, t, the inputs, is time. Find the average speed of the bike from 1 to 2 seconds. Now speed is the same thing as your rate of change of distance. Speed describes how distance is changing. So if I want to use the above formula, we could actually just say that A is 1 second and the B is 2. And that'll give us the average rate of change from 1 to 2 seconds. So that means I have to compute D of 2 minus D of 1, that's my change in outputs, divided by my change in inputs, 2 minus 1. In this problem, D of 2 would be, we plug the 2 in for t squared, so 2 squared is 4, and d of 1 would be 1 squared, or 1. So I'm going to take 4 minus 1, that's my change in y, divided by change in x, 2 minus 1. And that ends up giving me 3 over 1, or 3, and that would be feet per second. Now this is giving me an average speed from 1 to 2 seconds, but what if I want to know what was the speed from 1 to only 1.5 seconds? So let's do the exact same thing, but now my A is 1 and my B is 1.5. So I'm going to take a change in y divided by a change in x, and D of 1.5, or 1.5 squared, should be 2.25. So change in y is 2.25 minus 1, change in x, 1.5 minus 1, or 1.25 divided by 0.5, that turns into 2.5 feet per second. So that's my average rate of change, or average speed, from t equals 1 to t equals 1.5 seconds. Now, what I might actually be interested in is what exactly is my speed at exactly 1 second. Not from 1 to 2 seconds, or 1 to 1.5 seconds, but exactly at that one instant in time. And so the problem is, if we only have one time period, well, how do we compute slope? How do we find slope at only one time? And this idea here is we are trying to find something called the instantaneous rate of change, the rate of change at exactly one time. And this is also known as the derivative. Those two words mean the exact same thing. And so I have written down in my notes a limit definition of the derivative, or the instantaneous rate of change. And I want to show you where this definition comes from. You do not need to include this in your lecture notes, but I think it's helpful to know actually where these formulas come from. So in green, I've drawn some generic function, and I've labeled one point on that function. Its x value is a, and so then its y value would be f of a. If I have a second point on that line, I will be able to find the slope of the line that connects those 2 points. If I call the second point on my line b, f of b, then the slope would be the change in y values divided by my change in x values. The formula that I have just written down is the exact same thing as that average rate of change. So average rate of change is basically a slope through 2 points. Okay, I'm going to give that second point a slightly different name, just so I can derive the formula I have in the notes. Let's call that second point a plus h. So the idea is we basically just went over h units, and then its output would be f of a plus h. So now my slope is going to be change in y, f of a plus h minus f of a, divided by my change of x, which is a plus h minus a. The a's cancel out in the denominator, and I am just left with an h in that denominator. Now, if I want to find an instantaneous rate of change, if I want to know what is the rate of change just at that one specific point, what we're going to do is we are going to imagine, well, what happens if that second point gets closer and closer to that first point? And so the idea is we are going to let this h here go to 0. We want the 2 points to be at basically the same location. And so that's what this limit part of the definition is telling me. It's telling me that if I want to find the slope at one point, you start with 2 separate points, and then you basically just make the distance between them go to 0. And so the power of this limit formula is it's allowing us to find the slope at 1 point. And again, we call this our instantaneous rate of change or our derivative. Okay, so let's actually do the problem now. This is the part I want in your notes. The question says, what is the instantaneous speed or instantaneous rate of change of the bike at t equals 1 second? So my a here is 1. So using the formula, I need to find the limit as h goes to 0 of f, although I called it d in this case, so I'm going to say d of 1 plus h minus d of 1 all over h. And so let's start by finding d of 1 plus h. I'm going to take 1 plus h and plug that into my function. Recall, if you look at the top of this page, the original function we were working with was d of t equals t squared. I'm just taking the 1 plus h, plugging that in for t. And so that's why I'm squaring it. 1 plus h squared is the same thing as 1 plus h times 1 plus h. And if I multiply or FOIL that out, I end up with 1 plus 2h plus h squared. And let's see, d of 1, if I plug 1 into that function, 1 squared is 1. So back to my limit formula, I'm going to take the limit as h goes to 0 of d of 1 plus h. And we just figured out that is 1 plus 2h plus h squared. So that's my d of 1 plus h minus d of 1. And we computed d of 1 is 1 all over h. So I'm going to try to simplify this and then use the techniques that we learned in the previous sections to find this limit. So in the numerator, well, 1 minus 1 is 0, and I am just left with the limit as h goes to 0 of 2h plus h squared divided by h. Now usually with limits, we start by plugging the h value in, the number in. So if I plug in 0 for h, I get 0 over 0. This is my indeterminate form. This is the case where we have to do some more work. We have to do some more algebra. And in this case, the algebra I'm going to try to do is, I think I can factor the numerator. There's a common factor, or GCF, of h. And if I pull that out of the numerator, I am left with a 2 plus h. Now I can cancel that common factor out, and I am just left with limit as h goes to 0 of 2 plus h. To finish this problem, I am going to plug in that h equals 0 again, and I will no longer get something that's indeterminate. Instead, 2 plus 0 is just 2, and that is my solution. The instantaneous rate of change, or the instantaneous speed of the bicycle, exactly at 1 second, is 2 feet per second. Notice this is a little different than our average rates of change, because we had to look at 2 different times and essentially average it out, whereas here we're only looking at 1 time. I have many more examples that I'm going to do of finding derivatives or average rates of change using this limit definition, but I'm going to stop this video here and do those additional examples in part 2 of this section.